So now we're moving on to 4.2, classifying chemical reactions. In this section, which will be in two parts. So we are going to define three common types of chemical reactions: precipitation, acid-base, and oxidation reduction. Classify chemical reactions as one of these three types given appropriate descriptions or equations. Identify common acids and bases. Predict the solubility of common inorganic compounds by using solubility rules, and compute the oxidation states for elements and compounds. So the first part of this video is going to be the first four. I know that seems kind of weird, but that's because the oxidation states and then some extra redox balancing are pretty intensive, and I want to be able to keep that video separate so you're not overwhelmed, and each video isn't too terribly long as well. Okay, let's get started. So let's start by talking about some types of chemical reactions. The first one is called a precipitation reaction, and this is where you have dissolved substances reacting to form one or more solid products. So this is also known potentially as a double displacement, a double replacement, or a metathesis. I really don't know how to pronounce that word, I'm not gonna lie. Reaction. So generally what's happening is ions are being exchanged between ionic compounds in aqueous solutions. These are very, very common in nature and in industry. So some terms that we need to know, and you've seen some of these potentially from last section when we were talking about molarity and solutions. Solubility is the maximum concentration of a substance that can be achieved under specific conditions. Okay, so for instance, if you're trying to make iced tea, and you're trying to dissolve sugar in it, eventually you get to a point where you can't dissolve any more sugar in your tea because you've reached its solubility limit. If you have a substance that a relatively large amount of it can dissolve in your liquid, it is said to be soluble. For instance, in general, sugar is soluble in water. Now, you get a precipitate when solution conditions make it so that the concentration of solute exceeds its solubility. So I keep adding more and more sugar to my tea, and eventually I'm going to get a precipitate of sugar because it can no longer dissolve. So if you have something that has a low solubility, it is said to be insoluble. So it's going to really easily precipitate out of solution. So we have what are called solubility rules. And if you remember from last section, we looked at an equation, a net ionic equation, where we made silver chloride, which was a solid ionic compound in water. It didn't dissolve. We combined silver nitrate and potassium chloride to make the silver chloride solution. So we have rules for if an ionic compound is going to dissolve in water or not. I will also be posting a YouTube video that uses some mnemonics to help remember solubility rules. It's kind of cringy, but it works really well, and most of my students have enjoyed said video. So, some of our rules. Soluble compounds. So, while we do have some exceptions, these compounds most likely will be soluble in water. You have a group 1 metal cation or an ammonium ion. So your cation is either a group 1 metal, alkali earth, or the ammonium ion. It will be soluble. If it has a halide ion, so fluorine, chlorine, bromine, iodine, it'll most likely be soluble. If it has acetate, bicarbonate, nitrate, or chlorate, most likely soluble, same with sulfate. However, there are exceptions. For instance, halides. The halides of silver, mercury 2+, and lead 2+. If those are with a halide, they are actually not soluble. And that's actually because of the silver, mercury, and lead themselves. So if you were given AgCl, and I ask you if it's soluble or not, you would go, hey, that's a halide, but it has silver on it, it's not soluble. Some other exceptions for sulfates. So the sulfate ion is generally soluble in water unless it is coupled with silver, barium 2+, calcium 2+, mercury 2+, lead 2+, or strontium 2+. So those are the soluble rules and their exceptions. Now, there are some compounds that are generally always insoluble, with exceptions. So carbonates, chromate, phosphate, sulfide, and hydroxide ions tend to be insoluble unless they are with a group 1 metal, cation or ammonium. So ammonium carbonate, sodium chromate, those are actually soluble because of that group 1 metal. Or if you have a hydroxide of a group 1 metal and barium 2+. So those are also exceptions. So if you have an insoluble compound with a soluble exception, it's going to be soluble. We'll look at some examples and hopefully it'll make more sense. This table, one that actually I like a little bit better, is in your book, table 4.1. They just condensed it for the PowerPoint to make it a little easier and not take up as much room. So table 4.1 on page 183 has this table, just a lot prettier. So here's an example. We're given a molecular equation here. And what we can see is we've got some ionic compounds that are aqueous, and then we have an insoluble ionic compound, and then another ionic compound. So we see that lead iodide, or this is lead 2 iodide, is going to precipitate from solution. And that makes sense because we have a halide, however, it is coupled with lead 2+. Okay, so we can tell this lead here is a 2+ charge because the iodine is 1- and there's 2 of them. So if we were to bring this down to its net ionic equation, let's just kind of go through that really quick as a quick review. We break this up into its total ionic. We would have 2K plus 2I plus nope, not 2, sorry. Plus lead 2+ aqueous plus 2NO3- aqueous and that forms PbI2 solid plus 2K plus aqueous plus 2NO3 aqueous, and then we look and see K pluses cancel, NO3s cancel, and we get this net ionic equation. Lead 2+ and 2I- make lead 2 iodide. So this is actually what that lead 2 iodide looks like. There's lots of videos of people doing this reaction. I remember doing it in both second quarter when I took Gen Chem. We were quarter system chemistry, and also we did it in advanced inorganic chemistry. And it's a glitter. It's amazing. Just don't eat it. So here's another example. We're putting sodium chloride and silver nitrate together to make silver chloride and sodium nitrate. Okay, again, we can bring that down to its net ionic equation, and we see Ag+ and Cl- forming AgCl. All right, so here's an example. We want to figure out what is going to happen if we have these compounds combining, and so we want to say whether or not there's going to be a precipitate formed. So what we're going to do is figure out for what these formulas are and how they might be able to combine. So we have potassium sulfate. So sulfate is SO4 2 minus, potassium is K plus, so that must be K2SO4. And barium nitrate, okay, so barium nitrate, barium is Ba2 plus, nitrate is NO3 minus, so that means this has to be BaNO3 2. So our potential products we can make here, okay, would be, if we just basically we're switching the metals around. This is a double displacement, double replacement reaction. So basically what's happening, they're swingers. The barium is replacing the potassium is replacing the barium. So we could have potassium nitrate and barium sulfate. So barium is 2 plus, sulfate is 2 minus, so that would be BaSO4. And potassium nitrate, nitrate is 1 minus, potassium is K plus, so that would be KNO3. So looking at this, and we look at our solubility rules, we have potassium nitrate, we have a group 1 cation, that's going to be soluble in water. So that guy will not be a precipitate. But then we have barium sulfate. We have a sulfate which are generally soluble except when coupled with Ba2 plus. And this is Ba2 plus. So this guy is solid. This is a precipitate. So we do have a precipitation reaction here. So let's go ahead now and figure out our net ionic equation. This forms BaSO4 plus KNO3. I'm just going to write the solid by the barium sulfate, and I'm just going to assume, and just to save room for me, everything else I know is aqueous. So the first thing we need to do is balance everything in this molecular equation. If I put a 2 in front of potassium nitrate, now we're balanced. Yay. So then I get 2K plus SO4 minus plus Ba2 plus NO3 minus becomes BaSO4 plus 2K plus 2NO3 plus 2NO3 minus K pluses cancel, NO3s cancel, so we get SO4 minus plus Ba2 plus. Now I'm going to add my aqueuses in just for completion's sake. Becomes BaSO4 solid. So what you might also have noticed here is you can probably predict that net ionic equation without even writing everything out. You go, okay, well, I know BaSO4 is a product. That means that, and I know that potassium nitrate is going to be dissolved, so that means that it has to be the barium and the sulfate combining. So you might be able to just write down Ba2 plus SO4 minus becomes BaSO4. And that's perfectly fine. I just like to go through all the steps just to ensure everybody is following along. So let's look at this next one. We have lithium chloride and silver acetate. All right. So lithium, group 1. So group 1, so this is +1, so we have LiCl, since chloride is -1, and silver acetate. So acetate is C2H3O2 minus. Silver is generally always +1, so it's AgC2H3O2. So I'm just going to rewrite that over here. AgC2H3O2. So our products we can make here then are lithium acetate and silver chloride. So we actually should already know, because we've already looked at an example, that silver chloride is not soluble. We have the halide of chloride, but it's coupled with silver plus, so this guy is going to be a solid. The lithium acetate, though, we have a group 1 cation that's automatically going to be soluble. So for our net ionic equation, we know that the lithiums are going to cancel out on both sides, as are the acetates when we write everything out. So now we have Ag plus aqueous plus Cl minus aqueous yields AgCl solid. All right, now we have lead nitrate and ammonium carbonate. So we're actually not even hold the charge on lead, so that's fun. All right, we're going to assume they mean PB. We're going to assume they mean lead 2 nitrate, NO3 then, so we need 2 nitrates. And ammonium NH4 carbonate, O3 2 minus, so that means this is NH4 2 CO3. So then our products that we can make here would be ammonium nitrate, which is NH4 NO3, so we would need 2 of those to balance. And lead carbonate, PbCO3. So, looking at our products, we have an ammonium. Those are generally soluble. And it's with a nitrate, and nitrates love to be soluble as well. So that's soluble. And then we have lead carbonate. And carbonate is pretty much always insoluble. It's not coupled with an exception. There's no group 1 on there. There's no NH4. That's why NH4 ammonium carbonate is soluble, because that ammonium. So lead carbonate here is our solid. That is a precipitate. So all 3 of these are precipitate reactions. So we can see I've got 2 nitrates on both sides. Those are going to cancel. The ammoniums are going to cancel. And our equation is Pb2 plus aqueous plus CO3 2 minus aqueous comes PbCO3 solid. So now we were able to predict those products using our solubility rules and then do net ionic equations. Okay, so the next kind of reaction, we didn't really look at the reactions, but we've looked at acids and naming acids in chapter 3. So an acid-base reaction itself is, okay, before I really get into it, we're going to really talk about these way later. It may actually even be second semester. I can't remember if it's this semester or next. We're just scratching the surface with acids and bases and acid-base reactions. So bear with me. We are not getting into the whole rules. We're not talking about Arrhenius versus Bronsted acids and bases. Don't even worry what that means right now. We are just looking at very basic reactions. Okay? So an acid-base reaction, as far as we care, is where a hydrogen ion is transferred from one species to another. So we define an acid by something that can dissolve in water to make the hydronium ion of H3O+. So for example, HCl, so remember we put that in water, it becomes hydrochloric acid. Put it in water, and it gives that H to water to make this into hydronium. So it becomes Cl minus and H3O+. So since we transferred that H plus to the HCl, this HCl is an acid. Okay. Now, pretty much every single hydrochloric acid or hydrogen chloride molecule that dissolves in water does this. So acids that can completely react in this fashion are called strong acids. Okay, so every single acid molecule transfers a proton or H plus over. It is a strong acid. And there really aren't that many of them. This isn't all of them, but these are some of the most common ones. HBr, HCl, HI, HNO3, HClO4, H2SO4. Some of these you learned how to name. For instance, sulfuric acid, nitric acid, hydroiodic acid, and the acid halides. Notice though, fun fact, HF, hydrofluoric acid, actually is not a strong acid. We're not getting into why, we're not going to talk about that, but just a fun fact, it's actually a weak acid. And weak acids only partially react with water. So most of them stay together in their original molecular form. Only a small number of them allow a hydrogen to transfer over to water to make a hydronium. And there's way more of them. For instance, acetic acid, aka vinegar. You put acetic acid in water, you make a small amount of hydronium and acetate, and you have this double arrow reaction. We are not getting into this right now, but basically what it means is this is a partial reaction. It's a reversible reaction. If you see this and you're like, hey, look, that's an acid, and you see the double arrow, that's a big indicator it's a weak acid. Strong acids only go in one direction. Strong, weak go in both. A lot of fruits, okay, we have the citrus fruits, they have citric acid, which is a weak acid. Vinegars have acetic acid. Now, a base is a substance that will dissolve in water to yield the hydroxide ion, OH minus. Okay, the most common ones are the ones that have either group 1 or 2 metal. So we've already seen these before because OH minus is a polyatomic ion. Sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide. Okay, most of these hydroxides, okay, if they completely dissociate in water, they are a strong base. So this isn't a chemical reaction though, it's a physical process of them dissolving and dissociating into their relative ions. So again, remember, we just talked about dissociation for ionic compounds. These metal hydroxides are ionic compounds. You have an anion and a cation and an ionic bond. So this is not a reaction, sodium hydroxide becoming Na plus and OH minus. But because the sodium hydroxide breaks apart and generates OH minus, it is a base. We actually do have weak bases. Just like there's strong and weak acids, we have strong and weak bases. And these guys only partially react, but they can still form OH minus or lead to OH being produced. So for instance, ammonia, NH3, you put that in water, and what happens is water, okay, acts as an acid, if you will, and gives a H to ammonia, and we make NH4 plus, and that in turn generates OH minus. Okay, this is an acid-base reaction. I didn't really talk about it with the acids, but in those, water here is acting as a base. Okay, if you have an acid, you have to have a base. We'll talk way more about that later. Okay, here's ammonia used in fertilizers and used in cleaners. Now we also have neutralization reaction. And these are a very specific type of acid-base reaction. You react an acid with a base, and the products are a salt and water. And a salt, just as a reminder, is an ionic compound. Okay, water is not a reactant, okay, here at all. Okay, so while it can act as an acid or a base, depending on what's going on, that is not a neutralization reaction. You have to have an actual acid and a base. So for instance, if I take magnesium hydroxide and react it with hydrochloric acid, Okay, I make magnesium chloride and water. So the salt that you're making is you take the metal from your base and the non-metal from your acid, and you combine them using your rules for ionic compounds. Make sure they're charge neutral to make your salts, and then you should notice that you have OH and H left over, and from that you make your water. And you can figure out how many waters you make because, for instance, I have 2 OHs and 2 H's for the hydrogen, so that's 2 waters. Here's an example of a neutralization reaction that many of us may have seen. So fish has this wonderful compound in it called amines, and amines are smelly nitrogen-containing compounds. Literally, this one that many fish emit is called putrescine. I'm not making this up. There's even one that I knew I had when in grad school. I had a lab mate who worked with amines, and he worked with one called cadaverine. I wish I was making it up. They smell awful. But when you squirt some lemon juice on your fish, you might notice that that odor and even maybe that kind of gross taste, it goes away. And it's not just because lemon might taste good. You're actually doing a chemical reaction. The acetic acid in that citrus reacts with the amine to form this salt here. Okay, you have this negative charge from the acetate, and then the putrescinium ion is positively charged. Okay, then of course you have the water product as well, but you make this salt here that then is odorless. Sorry, I know I'm like super geeking out right now, but I just have always thought that's really cool. This is why citrus is so great for things like fish. Okay, so now we're going to talk about oxidation reduction reactions. These are also known as redox. Chemists are lazy. I don't want to keep saying oxidation reduction. Saying redox is way easier. It makes it sound kind of cute. So we're almost to the next video, but not quite. So redox reactions involve the transfer of electrons between reactant species. Okay, and they generally are going to make an ionic product. Not all of them, but most of them. So one thing we can do is split this reaction into individual equations called half reactions. So for instance, looking at this original equation, 2 sodium metal and chlorine gas form sodium chloride. So we know that sodium chloride would be 2Na plus 2Cl minus. Ignore the fact that it's not dissolved in water, it's making a solid. This is just the ions that make up sodium and chlorine. And so, that make up sodium chloride. Ugh. Okay, so we can kind of zoom in and focus on each thing that's happening here. We can say that 2 sodium metals become these 2 sodium plus ions. So that's a total of positive 2 charge, since I have 2 positive ones. And there's 2 if we put 2 electrons here, so that's plus negative 2, that's overall 0. And on the left side, we have a total of 0 charge because the sodium, there's no charge on a block of sodium metal. And then we also have chlorine gas. Okay, this is just 0. There's no charge on this chlorine here. But it's becoming 2 negative 1 chlorine. So that's a total of negative 2 charge. Okay, I can't add 2 positive electrons. There's no such thing. Well, yeah. Don't come at me, physics people. But I can take 2 electrons and put them on this reactant side with the chlorine, and that gives me a total of negative 2 charge on the left. So if you notice then, kind of get rid of all this crap in the way, if I were to add up these 2 reactions, the 2 electrons cancel out, okay, and we would get what we started with, 2Na plus Cl2 gas, we can go back to saying 2NaCl solid. still adds up. Okay, so this is how we do half reaction. And what you should see here, though, with these half reactions, coming back to these, is the electrons for sodium are on the product side. Okay, meaning that sodium is giving them away. It's losing electrons. Whereas chlorine, the electrons are on the reactant side, meaning it's gaining electrons. So sodium is giving its electrons to chlorine, transferring the electrons over. Okay? Now, when we have redox reactions, these terms often get confused. People get them mixed up. Oxidation means that you are losing electrons. Reduction is gaining electrons. Okay? So we have some sayings in chemistry to help remember. Oil rig is the main one. Oxidation is loss. Reduction is gain. And we also have Leo the lion goes grr. Lose electrons, oxidized, gain electrons, reduced. Okay, so in our reaction, sodium lost electrons. They were on the product side, so it's oxidized. Chlorine gained electrons, so it is reduced. These terms will make a little bit more sense in the next video. Now, sodium is oxidized, but it can be called the reducing agent or the reductant, okay, because it causes the chlorine to reduce. It gives chlorine its electrons. Chlorine is the oxidizing agent or oxidant because it takes the electrons from sodium, it forces it to oxidize. I know it's kind of some weird terms, but bear with me. Practice makes perfect. You guys got this.